Welcome everybody again. Okay, this is the third part of classical Hodge theory. This will take us to hopefully to prove or at least to know how to prove the Hodge decomposition theorem. So let's remember a little bit what we did yesterday. What we did yesterday is that we show that using a lot of linear algebra that when you take the alternative product of the complexifications of the duals of the tangent bundles, I mean the cotangent bundles in this case, when you take the dual, then you get a direct sum decomposition of certain spaces, and these spaces are nothing but well, you have R times the decomposition that we got for remember that originally we wrote I mean the cotangent bundle, at least in a point, as a direct sum decomposition of these two, right? And so you have these R times here, and then you have S times the duals, right? I mean the other ones. And so this indeed, this space here is actually, as we saw, is a complex vector bundle. And its sections are the differential forms, right? And this is kind of, we have to be careful with this. I denoted this by A to the K. It depending on, I mean, you have a section depends on where you take the section, could be the whole M. M is a compact Riemannian manifold, complex in this case. We still don't need the Riemannian. So these are C infinity differential forms with complex values. So remember when I had real values, I put R after the set here, right? So what the decomposition above tells us is that you can decompose any K form as a direct sum of forms of type RS. I didn't say that yesterday. So these are K forms of type RS, right? So when you take a sum of them, you get the whole space. And I didn't say something very important yesterday because I was in a hurry at the end, is that I didn't say anything, since we are in the complex world, I didn't say anything about what is a holomorphic differential form then. Okay, for that you should take the first one of this, right? So in our case, okay, we take the K0 forms in the whole M, for instance. And these sections is what we call the holomorphic forms, right? And usually we use this notation here, or some other people use this notation. Or if you take an open subset, this is better because if instead you take this, then holomorphic sections over U are denoted usually by omega K, right? So everything else I said is right. And then one thing I said very rapidly at the end is that when you have the double complex, right? And so you take this and then you take partial bar, etc. Then I said very quickly that this is the kernel of this map is actually the holomorphic forms, right? And I think I have okay, and then this thing, the fact that this thing is a kernel, it is not as straightforward as it seems. You need to do something like, you need to prove this. We're not going to do this, but I mean, this could be, basically, this could be our definition of holomorphic forms, right? But this don't do that. And finally, what I did at the end is that I defined the double cohomology groups as I said, closed with respect to partial bar PQ forms divided by the exact forms. PQ minus 1, right? With respect to partial. Okay, so so this is what we got at the end. As I said, this is an invariant. This module is an invariant that depends on the complex structure, because recall that we are using heavily the fact that you can decompose the differential as the sum of two differentials, one that moves the holomorphic part and the other one moves the anti-holomorphic part. And actually, some people take, some books use this as the definition of an integral manifold. I use a different one, but they are both equivalent, right? Okay, so just for those of you who know a good deal of complex geometry. So, okay, so now we want to define now what a Kler manifold is. So let's take a complex manifold. With complex structure J. And remember, when I say complex structure in this way, I'm referring to the map that takes vector fields to vector fields. You remember that? So I mean, not the structure as a manifold, but as a vector space, the space of derivations, right? So if you take a complex structure and Riemannian metric, let's call it G or M, then we say that G is Hermitian, a Hermitian metric. If when I take the Riemannian metric and apply it to two vector fields, but I change the first one by the complex structure, I get the same thing. And this should be for all point and for all vector fields, right? So that's a Hermitian metric. So another way to put this is like, I mean, you can define a new form by taking G of JXY, and then this omega is actually it's a two form, but actually it is real. It is okay. Actually, we can prove that it is a real 1 form, right? So actually omega is in A11, right? So, and I'm gonna put everything now, since it is real, right? The conjugation of omega is the same. This is not W, this is omega, right? To know this, you have to use the properties of the Hermitian metric, and this is more linear algebra, right? So what is important for us is that in local coordinates, you can see that a form looks like, I mean, this form given by the Hermitian metric can be written as something like this. You have some coefficients here, and then you have, well, it is a 1-1 form, so you have something like this, and J and K vary from 1 to n. N is the dimension of the complex manifold, and then you also have one property, since it is a real form, you can write the coefficients and know that this is the same as HJK bar to conjugate. So it turns out that as a metric, G is positive if and only if the matrix you get by considering the coefficients in the local coordinates decomposition, if this matrix is positive definite, right? Right. So we are again in the world of linear algebra, and so we say in that case that omega is positive, right? So another definition for Hermitian metric is that M has a Hermitian metric. So here, if it has a positive positive definite, I mean, locally like above, one real form, right? So finding Hermitian metrics is the same as finding this kind of forms. That work globally, of course. And so we are now ready for the main, one of the main definitions of this course is that, so you take a complex manifold, then a Hermitian metric scalar if and only if the corresponding 1-1 form is closed, right? It's closed with respect to the inner derivative, right? So so M is scalar if it has a Kler metric and in that case omega is called a Kler form, right? So whenever you take, again, so what is the order of ideas? You have a Hermitian metric on a complex manifold. You can always assign the 1-1 form, but that doesn't necessarily mean that the form is closed with respect to D, right? So if it is closed, that will be called a Kler metric. Okay. So one easy consequence of this is, for instance, that if M is a compact Kler manifold, then let's see. Then if you take all these groups, right? Then they are not empty. Then the dimension of this group is not 0 when K is goes from 0 to the dimension of N, right? So this is a very interesting fact that you have by imposing the Kler condition, you can say, well, this is very important. A lot of things about the cohomology groups of the compact manifold. Okay, so another important property is that I'm gonna use this later when I define the fundamental class, okay, of a manifold. But anyway, another important property is that if N is a complex of manifold, if M is a complex of manifold and M is scalar with a Kler form omega, then N is also Kler. With Kler form, who do you think is gonna be? It's gonna be omega restricted to N. So what am I stating these two properties? Because this one, the second one is very important because we have what I want to call the example. I haven't been given a lot of examples, but in the sessions in the afternoon, we have. I mean, you have been attending those. You can see that. But so the example for us is so what is this? The example in for those who are interested in algebraic geometry is that it's projective space, right? I'm not gonna say a lot about it because I think that is something that everybody knows. And when I say projective space, I mean in complex projective space, right? Why is so important for us? Well, for several reasons. First of all, projective space is a compact complex manifold, right? And if you if you never did this, it is a good time to say that it is important because it is the first example, even in the real case, of a manifold that it doesn't look like the Euclidean space. Okay, so in the complex world, it is a compact manifold, but it turns out that with something called the Fubini study metric, it is scalar. So this is an important example because it is compact, it is a manifold, but it's also scalar. And now I'm going to use the proposition. If you take a submanifold of projective space, this one is called a complex projective manifold in general. And by the proposition above, M is scalar. So now we have a huge box full of examples of scalar manifolds. All complex projective manifolds are scalar. Okay, so we have a huge world to work with, right? And that's the reason a lot of people states the Hodge theorem and the Hodge decomposition just for projective manifolds, because we have a lot of examples there. But on the other hand, not all compact manifolds are scalar, right? And we saw an example yesterday in the afternoon session. All right. But now, again, talking about, before stating the Hodge decomposition, well, we need more material than this. But again, if you come from algebraic geometry, you are interested in algebraic varieties. So the question here is that, okay, clearly a smooth complex projective variety is a compact complex manifold. Right? So you can take all your favorite examples of complex projective varieties and you get all what we have said today and the days before, right? But what about the other way? Like, why do you start with a compact complex manifold? When does it have a structure of an algebraic variety? Well, that's the answer is given by a famous theorem by Chow theorem that says that actually Chow theorem is more general that the thing I'm going to say, but this is an easy consequence of Chow theorem. But let's put it this way. Let's just start with, I'm gonna use now X because I'm trying to say that it's a variety. So let X be a compact complex manifold. And suppose there exists a holomorphic embedding from X to projective space, right? Then Chow's theorem say that X is a projective, I should say smooth projective. The right way is to say this one. It's a smooth projective variety. Okay. What I mean, algebraic, right? So that gives a full answer to where to look. right? So, okay, so now we started with real manifolds, then we moved to complex manifolds, and then I stated what a Kler manifold is, because now I want to say something else about the RAM cohomology groups, right? So let's remember a little bit what we did before. So we will be talking more about algebraic geometry later, but at first we can use this result now. I mean, we can restrict all our results. So you don't want to remember what Kler is later, you can just talk about complex projective varieties, smooth complex projective varieties, okay, for the moment. And then what is what we did? Remember that we had this is something we did before, so I'm going to just state it quickly. We started with a compact, oriented, and dimensional manifold. And by this, I mean also smooth. And then when you translate this to the world of complex manifold, our complex manifolds by the complex structures are always oriented and even dimensional. And so let's add the fact that we have Riemannian metric G, real in this case. I mean, here I'm referring to a real smooth manifold. Then remember what we did before is that we have the Hodge operator. That was an operator, well, you can see it in two ways, from this space to this space, or from the space of real forms, C infinity real forms. I have a mistake here, right? This is something we already introduced before. And then once we know the Hodge operator, okay, something I didn't say before is there's another way. I didn't say this before. Is to define the Hodge operator by a property like that the wedge product of what the so-called star operator is going to be, it should be something like this is the main property that characterizes the star operator. This is a more abstract way to put it instead of using basis. And this big omega, he is the volume form, for those who know what this is. So this is another way to characterize the Hodge operator. Some people, and remember that I define this inner product as this, right? And then, okay, it seems like a circular definition there, but it's not. Oh yeah, I know. This is the inner product given by the metric G. Okay, so once we have, in any way you define the Hodge operator, we can define this product we use a lot, which is a positive definite inner product. On some people call it an L2 inner product. It doesn't matter for us. This is an inner product on any of the spaces of forms, all right? So we did this before, and remember that we also associated to this, we have another operator that goes in the opposite direction of M, and this is the formal, this one here is the formal adjoint of the exterior, the exterior derivative. What I mean by formal adjoint, remember again, is that have something like this. And then once we have this, we define the Laplace Beltrami operator, which was nabla, that goes from the space of differential forms to the space of differential forms, and was defined by taking to any form you should compute, you remember, the derivative, the adjoint, the form plus the adjoint, the derivative, the form, right? So actually, we also showed, or at least I said, that this operator, this one was an important property. This is self-adjoint. And by self-adjoint, I mean that when you take the product we defined by the integral, then you can sort of solve for any of the parts in the inner product. And then a new proposition that I didn't state before, but I think I should state it because in the afternoon sessions, someone asked about the why is nabla equal to 0 the same as the components being 0. So a proposition I didn't state before is that when you take the commutator, then this is 0. With D as well, of course. And also with the star operator. This is a new property I didn't state before, but perhaps it is better to put it this way because now it's going to be clear inside the proposition that this is 0 if and only if both operators are 0, right? That's another way to prove it. And but I mean by the bracket there, this is called also a commutator, is that you have two things here. This is d1, d2 minus d2, d1, right? So again, remember that a form is harmonic if the Laplace Beltrami operator is 0, right? So, okay. So another proposition that I didn't state before is the following. I didn't say this, and I think it's very important. A closed R form is harmonic if and only if when you take the norm with respect to the inner product I defined just above, this is a local minimum. In the RAM cohomology class of alpha. That's why we need functional analysis, because if you know functional analysis, you know that a problem of minimization is solved by projections, right? If you have had courses in functional analysis, that's the way to solve it, right? That's why we need the Hodge theorem to write the space of harmonic forms as a direct sum. And you know that whenever you project, you get a minimum. That's the reason. So we can actually prove before that that a form is harmonic if it is a local minimum as a cohomology class. Okay. So this is new, but it's very interesting. Actually, as part of this theorem, we already knew this in the RAM cohomology class. Has at most one harmonic form, right? So there is at most one representative that is harmonic, right? And so the question is, the RAM cohomology class has at least one harmonic representative. By the theorem above, we know that it's going to be unique. The answer is yes, and we know this because we already stated the Hodge theory, right? That's a consequence of the Hodge theory. And again, since a lot of people have asked, remember that the proof of the Hodge theory uses elliptic differential operators, right? So that's a quick summary of what we did in the first 2 days. So the RAM cohomology can be identified with the space of harmonic forms. But now we are in the complex case, right? Now we have a complex manifold with an almost complex structure, and let's suppose that the manifold is scalar, so with scalar form. So it's a compact, and it's also compact, right? Complex, and being complex, it has a complex structure, and being scalar, it has a scalar form, right? So what if we apply, we have new groups now, right? Remember, when you have a form, you can write this as a direct sum of forms. So let's suppose that the dimension of our manifold is n, the complex dimension. So what if we apply the star operator to a Hodge operator to one of these subspaces, right? Well, again, this is a fact. I'm going to state what the answer is. So this is going to be something in here. So again, this is more linear algebra. Right? That's why some people prefer the definition I mentioned at the beginning, using basis instead of the definition with the volume form, because you can restrict everything to linear algebra, and then you get the statements like this, which are easy to get, right? So with this at hand, then it turns out that, well, we already knew this property. The adjoint of D is given by minus star D star, right? Well, here I'm using the fact that the manifold has even dimensional real dimension, okay? because when I stated this property, I had some exponents here, but it doesn't matter. It gives you this. And then, but now we know that D is a sum of the operator acting on holomorphic forms for plus an operator acting on anti-holomorphic forms. So this would be minus star, partial star, minus star, partial bottom, partial. This is the right order, even if it doesn't seem so, but when you apply the star, it changes the order. And then we have now two operators again. We have, sorry, let's call partial star to the operator given by the first summand. And let's define nabla, sorry, not nabla, it's partial bar star as the operator given by the second one, which is minus star partial star. So I'm going to stop here, just stating the main proposition for this is that it turns out that partial star is a formal adjoint of partial. Remember that here, this partial was partial bar, right? So the other one is a formal, adjoint of partial bar, right? Where in the Hermitian extension of the inner product to the space of forms, right? Remember that I define above the inner product for real forms. So you can easily extend this to the complexification, okay? So with respect to that inner product, they are formal adjoints, okay? Okay, I'm gonna stop here. Do you have a break of 10 minutes? We will be back. Okay, let's continue with the lecture. So once we know that these two new operators are adjoints of the components of the exterior derivative in the complex case, we can now do something similar to what we did before. For instance, we can define a new type of Laplace Beltrami operators as well. For instance, for the first one, for the first one, we could define nabla of partial as partial star plus partial star partial, and the other one in a similar fashion should be something like for the partial bar should be bar star plus bar star, okay? And so we are not doing anything new because it turns out that the Hodge theorem remains valid. What do I mean by this? That that you can define the space of PQ harmonic forms with respect to, for instance, the one we are using for the Ball cohomology, which is partial bar, and you can define this of M as the PQ forms PQ complex valued C infinity forms, such that when you apply the Laplace operator to alpha, but not any Laplace operator, the Laplace operator with respect to partial bar, then you get 0. These are the, let's call it the Laplace with respect to, it doesn't have a name, the Laplace with respect to partial bar or harmonic forms, right? And so what do I mean by the Hodge theorem remains valid? Well, in this case for us, what is important is that when you consider the double cohomology group of M, which I defined above, then actually this is the same as the space of PQ harmonic forms, right? With respect to this operator, okay? So this is not a new proof. It's the same proof. It's just that now we use this operator instead, because remember that they are C infinity forms. Even if they have complex values, that's a small change, but all the other things are the same. And that's why in some books they don't treat the real case, because why do it twice when you could do it for the complex case as well at the same time? Okay, so now we are almost there. Because now we are almost there to state the Hodge decomposition theorem, because now let's consider now a Kler man. If M is scalar with form omega, we have an operator. I'm not gonna stop a lot in this operator, but we have an operator that goes from the space of forms to the space of +2 forms. And this is called the Lefschetz operator. That what it does is that there's a whole theory of this, but I'm not going to talk about this in this course, but it is important anyway, that takes the wedge product of the form with the Kler form, right? So as an operator, it should have an adjoint. So let this here be the adjoint of L. I mean, adjoint related to the inner product. And then a theorem we have with respect to this theorem is an important theorem called the Kler Identities. Says that don't worry if this is too technical, because it seems like it is. It actually is, but it is very important later. So actually immediately afterwards. So the Kler identities are, for instance, you take partial with L. I'm gonna forget the omega for a little, and you get the commutator the other way. They are the same. And if you take the commutator with a, let's say, partial star with respect to this adjoint, or if you take the commutator of partial bar star with respect to the same adjoint of L, these are all equal to 0, for instance. Or for instance, if you get, if you take, sorry, for instance, the bracket of, well, this is not the bracket, it's a commutator. You take the commutator of partial star bar with respect to the Lefschetz operator, then you get, this is important, you get the first component of the exterior derivative multiplied by I. Or if you take, let's say, you take just this one here with respect to L, you get minus I partial bar. What else I'm missing? Oh yeah, if you take partial bar with respect to the adjoint, you get I partial star, and you get finally 1, 2, 3. Finally, I'm missing one. Yes, you take partial with respect to the adjoint of the Lefschetz operator. You get this is more complicated. You get minus I. No, it's the same thing. Partial bar adjoint. Okay, so we have these technical, very technical identities, but they don't have a name for nothing, because actually as a corollary of this, we can say that if M is compact scalar, actually from the theorem above, then we can show that the Laplace Beltrami operator is actually twice the operator on given by partial bar, okay, d bar. So why is this important? Because we can, I mean, we already knew a little bit here above, right? That when you, let me go back a little bit here. When we have this identity, this isomorphism here, we know that something is going on and that these are part of the whole RAM group. So let's state that clearly here. So using this theorem, what if we take a complex form? Actually, let's take it a closed one. So let's take a harmonic form here. But I'm thinking of harmonic forms with complex values. Then what happens if I take a form there? Then I know that the harmonic forms have a direct sum decomposition, right? So I can write this form as it has a K0 part, it has a K minus 1 part, etc., right? Because we know that you can decompose a closed form in this way, right? Actually, it doesn't matter if it is harmonic or not. You can always write this decomposition, right? But then the components are, since they are harmonic, are nabla partial bar harmonic. And by the theorem above, since the Laplacian is 2 times this new operator, then they are harmonic as well, right? In the original sense. So that means that you can separate, the space of harmonic forms as a direct sum of PQ harmonic forms, right? Where who are these spaces? H, P, Q, M is actually, you have to take the space of harmonic forms with complex coefficients and intersect with the PQ forms, right? Because, and moreover, actually, by the properties above, H, P, Q, if you take the conjugate of this, this is H, Q, P of, this H, Q, P of. So what I'm saying is that I'm going to go above a little bit here. So this decomposition is linear algebra, right? So what I'm saying here is that you start with the composition on the space of forms. And from this, you get the decomposition on the space of harmonic forms. Right? So this is not an easy thing because we are passing from the space of forms to a cohomology group, and passing to cohomology is not an easy step in any case. But what happens for a Kler manifold is that it is an easy step, right? So all this is because M is scalar. So that decomposition we got with only linear algebra passes to cohomology using the fact that the manifold, the complex manifold, is compact Kler, right? So, but again, by the Hodge theorem, right? We know that the space of harmonic forms is the same as our group, right? So I can state now the big theorem of this course is that this is the Hodge decomposition theorem. That says that if we start with a compact Kler manifold, then if we take the RAM cohomology group of M with coefficients in C, then this is the same. I mean, you have a direct sum decomposition of this as a sum of certain spaces where these spaces are such that when you take, well, what they are, who are they? They are isomorphic to H, P, Q, M partial bar. That, as we know, they are the space of harmonic forms with complex coefficients. And what else? We also know what is important in the Hodge decomposition is that when you take the conjugate, you get H2, right? This is a famous Hodge decomposition theorem. So, what else? Usually, when people uses Hodge theory as a black box, they usually state the theorem directly. And usually they don't even mention Kler manifolds because you can state, as I said before, you can use just projective, smooth projective varieties, right? So in algebraic geometry, usually they say, okay, let's start with a smooth complex projective variety, right? So that's why we can do it. But in general, it works in a more general setting, works for any Kler manifold, okay? So actually, there are some things above that I didn't say that work in the general setting or symplectic manifolds, okay? Not all of it, okay? But if you are interested in digging into the deep of the theories, even some identities, you can use the fact that the manifold is symplectic and work on it, right? But anyway, let's forget about it. So now we have more definitions at hand. We can define HPQ as the dimension, the complex dimension of these new spaces we are introducing. And these are called Hodge numbers. Sorry. And what is the relation with the Betti numbers? Remember that the Betti number is a dimension of this. And so these are the Betti numbers. So what the Hodge decomposition says is that you can write this as a sum of the Hodge numbers, right? And well, an easy consequence is that since we have the conjugation property, is that the odd Betty numbers of M are even, right? That's an easy consequence. Okay. So I'm not going to say more about this, but for people interested in applications, this is what they look for, right? They look for a way to calculate the Betty numbers. For a full discussion on how to calculate this in some cases, I invite you all to the session in the afternoon where Roberto, well, he started already yesterday with some examples of calculations, but he's gonna tell us more, right? In the afternoon. So don't miss the class in the afternoon. You can see applications of this stuff, right? So okay. So now that we know the Hodge theorem, I can talk about, so remember here, the Hodge decomposition theorem tells us that whenever you have a compact Kler manifold or a smooth complex projective variety, you have a decomposition. And another important property is this one, right? So now we can introduce Hodge structures abstractly. Okay, so to introduce Hodge structures, I have to make more definitions. So we're talking about the formalism now, right? So now we start with a subring and a Hodge structure is nothing but some people use this abbreviation of weight. Let's call this weight K is given by well, here K is an integer, could be negative. It's given by, okay, it's given by what? One. A finitely generated A module B and two, a decomposition. What decomposition? A decomposition like the one above. A decomposition of the form. Now is when linear algebra phase. It is you need to stay to take the complexification of vector space, and then you should have a decomposition on the complexification. Right? Such that when you take the complex conjugation for each of the components, you get the other one, right? So that's a Hodge structure in general. Another way to put this is to use equivalently, we can instead of using 2, we can use 2 prime, which says that we have instead of having a decomposition, is given by a finite descending filtration for the complexified space. Satisfying that BC is equal to, okay, I always forget this, is FR plus if the dimension of the manifold, no, okay, I'm not talking about it. It's K minus R plus 1 conjugate for all, for any integers R, right? So instead of, how do I go from one to the other? How do I go from a complex from the decomposition to the filtration? You can ask. Well, that's easy. This is defined by taking the sum of PQ, P plus Q equal to K, and the first one should be bigger than K, right? That's the way you go from 2 to 2 prime.
You mean R?
Yeah, you're right. Sorry. K is the weight of the Hodge structure. So yes, thank you.
The other way around. Sorry, P plus Q is K, but P is.
Yes. Now, okay, thank you. And then the other way around, it is also easy. You want to go from the BIS definition to the original one. Well, it doesn't matter which one you take. You can define BPQ as FP intersection with FQ bar, right? So yeah, they are both indeed equivalent. Now you can say, why do you introduce filtrations when we already have? I mean, now that you know the Hodge decomposition, now you are rightfully thinking on your example, right? And actually, as I said yesterday, when we stated the decomposition for the alternating space of forms, we already had one. So one of you could ask, why are you thinking of filtrations when you can just stay with the decomposition? Well, the reason is because when you enter in the world of variations of Hodge structure, the way to see how a Hodge structure varies on family, it is better to use the Hodge filtration, right? This one here is also, I didn't say that, but F is called the Hodge. Right? So even when for us, it is not like very clear way to use it, believe me, this is very important in other settings, right? And sometimes even preferable. So we should keep it there at hand. Okay. So in any way, they are the same. You can go from one to the other pretty easily. Now, there are some other. I took the most general definition for a Hodge structure, but some books actually good with things like, for instance, they forget about any. They don't talk about any ring. Actually, they take the ring to be the reals, and this is what they call in this case we say we have a real Hodge structure. So in the condition 1, we can change finite generated by vector space, right? So and similarly, some people, instead of taking R, they take an intermediate step and they take the ring of the rationals. And in this case, we call of a rational. We talk about a rational Hodge structure, right? Again, we use vector spaces in this case. But another example, which is very extreme, is to use the integers. This is called, obviously, an integral Hodge structure. And instead of vector space, we use the fact that it's a lattice, right? Instead of taking a vector space, we take a lattice, right? Now, what else? We can define morphisms of of Hodge structures of the same weight. Right? What we do is that they are compatible with the decompositions. So for instance, in the case of a real Hodge structure, you actually need a linear transformations that takes the component PQ to the component PQ, right? So what I'm trying to say is that Hodge structures of the same weight form an abelian category. All right. And so what is the main example here? We know it already. Is to take X, a compact scalar complex manifold, or as I say, a complex smooth projective algebraic variety. And then we know that when you consider that variety as a compact Kler complex manifold, then you can take the RAM cohomology group. And we already know that the complex Dirac cohomology group is actually, well, the Hodge decomposition tells you that this is, sorry, this is actually the sum of the PQ space, right? Okay, so the weight, and actually we need more, actually. We already know that this is HQ. Right? So what else? If H is a Hodge structure of weight N and H prime is another Hodge structure of weight, a different weight, let's say M prime, then what we can form more Hodge structures. For instance, we can take the tensor product of Hodge structures and get a new Hodge structure. It's a Hodge structure of weight M plus M prime. And we can even take, as we saw, morphisms, but then we take all the morphisms between H and H prime. And then it turns out this is also a Hodge structure of weight. And minus. So we have an inner there, right? These are more examples of Hodge structures. Whenever you have two, you can do these two operations and more. You can even, well, once you have you have a full set of tools. Another one that is very basic is the Tate. Tate Hodge structure of weight -2 that is given by, just consider your lattice as, let's say you take the integers and you consider 2 by I. So you have a lattice there. And then this is a lattice, of course, in C. And so you have to define what the Hodge structure is. Well, okay, let's define it. You take directly HC to be just the one component, right? You define it directly. And so this Hodge structure is denoted by C1, right? Why by C1? Because then you can take Cm, which is actually to take the tensor product m times of C1, and this is a wedge as a Hodge structure of weight minus 2m. This is it seems like I'm saying nothing, but believe me, that is technically is very important to introduce state Hodge structures to make things work when you have different weights. Okay, that is important when you take, for instance, the chart class and so on. And so in the, even if you don't take the, if you don't know what the tensor product is, you can do it directly, right? Because then what would be HC would be 2 pi I to the m of C, and then the only component of the decomposition would be minus m, right? You can do it also directly. So once we have, again, if, okay. If we take a Hodge structure of weight n, a twist of H is a new Hodge structure of weight n minus 2m, given by, what do you think is going to be? Well, you only take, again, you take your Hodge structure, well, the integer part, integer. So you take H C, and then you take 2 pi I to the m, right? That's a way to change the weight of the Hodge structure accordingly to your needs. Okay, and so what would be the decomposition then? Would be H m p q, would be H plus m q plus m, right? And we can also define morphisms of type RR, which go from a structure of, from this structure to another structure, but you have to change, you have to introduce a twist so you get something in the same. So that the definition agrees with the definition I gave for morphism of Hodge structures. I mean, if they have different weight, you can always move things a little bit with twists, so you have something that goes to the right weight. Okay. Okay, I'm gonna stop there. What I'm gonna do tomorrow is that I'm gonna, okay, I talk about the Hodge structure of the rank homology group, right? And I say, okay, we have let's say, yeah, smooth, X is smooth, complex, projective variety. So to finish the course, I'm gonna go more into the realm of algebraic geometry, because you can say, what if I take away the projective condition? What if my algebraic variety is not projective? Let's say it's just compact. Can we still get a Hodge structure in the cohomology groups? The answer is yes. You have to change the RAM cohomology group by the Betty cohomology group. But that's fine, because in the projective case they are the same. But what if you now not even have compact, and you have only this seems like a stack, right? Why do you only have smooth variety? Can you still introduce a Hodge structure? The answer is no in general. But we can still do something, and that's mainly the work of the lean, because even if the variety is not smooth, you can still put on something called a mixed Hodge structure, right? And so that's what we are gonna, I'm not gonna construct them because we don't have time, but I'm gonna tell you what that is. But we're gonna start with this case. We're gonna start with a compact, smooth, complex projective variety. And then I'm gonna talk about at the end how to say things for complex varieties in general, even if they are singular, okay? So thank you all. See you in the afternoon for examples on how to compute Hodge numbers with Roberto. Thank you.